In this problem, we want to describe a sphere centered at the origin with a radius of 3 for a triple integral in rectangular, cylindrical, and spherical coordinates. And we're going to start with rectangular because that's the most familiar. Because of all the symmetry, we can pick whatever order we want. So I just went with the integrals x, y, and z. So I wrote an integral dz, dy, dx. Remember that the last integral has to be constants, but the early integrals can be functions of upcoming variables. The early integrals can involve functions of upcoming variables. So the bounds on z can have functions of x and y. The bounds on y can have functions of x, and x is going to have to be constants. So if I imagine this sphere sitting with the center at the origin and a radius of 3, the easiest thing to grab is going to be the x values that the sphere is between. The lowest x value will be at -3, the largest x value will be at +3, and that's always why I get the last integral first. Now I'm going to start breaking it down into the up and down, and then the right and left. So in the up and down, that's the z's. If I solve the equation for z, we get z equals plus and minus the square root of 9 minus x squared minus y squared. So this represents the top and bottom hemispheres. That's the surface of the top and the bottom of the sphere. So we can integrate the z's from minus the square roots of 9 minus x squared minus y squared to plus the square root of 9 minus x squared minus y squared. Now I'm going to look at the sphere from the top down. I've got the z's taken care of. Now I have to describe what's going on in the XY plane. So I'm going to look at a top-down view. So I'm just going to grab the x-axis here. I'm going to spin it so it points down, and then I'm going to twist this so z comes straight out the paper. So I'm going to look at this from the top down, and it's a sphere, so it always looks the same. I think that second one helped a little bit. There's the center. So there's the y-axis, and then here is the x-axis now. Here's our 3/4 view. Here's our top-down view. 3/4 view, top-down view. GTA 5, GTA 1. We've already taken care of, since we're looking top-down, we just care about describing all these points. We've got all the z's between the bottom of the sphere and the top of the sphere. So we see the top of the sphere up here, and I'm using opaque paper so you can't see the bottom of the sphere down underneath. You also can't tell that my pen's making these like little circle shapes going down and then up again. I don't know, maybe you can. Or maybe your internet connection is too slow to see the pen move this fast. So what we need to do is describe what the y values are between. So we've already said the x's are going to go from -3 to 3. We just need to describe what for a given x value, what are the y's between. So we're looking at this circle, and in the xy plane, this circle is going to be x squared plus y squared equals 9. X squared plus y squared equals, the circle in the xy plane will be x squared plus y squared equals 9. And then there will be smaller circles above and below. So I need to pick a generic x value and say, what's it going to be between? So this circle in the xy plane is x squared plus y squared equals 9. So we're going to go from negative square root of 9 minus x squared to positive square root of 9 minus x squared. That'll give us the left and the right part, halves. Any questions? What's z between? What's the y between? And what's the x between? Any questions or comments? Snide remarks? Confused looks? Remember, if you're trying to communicate through facial expression like we often do in class, it's not going to work because I cannot see you. All right. What we want to do next is practice describing this sphere with cylindrical and spherical coordinates. One of them is going to be very good at describing this sphere. Which one do you think is going to be very good at describing this sphere? Which set of coordinates will be best for describing? I should have asked that first. We're talking about it. We're talking about describing a sphere. What set of coordinates will be best? Probably spherical coordinates. So let's do that one next. So I want to describe a triple integral in spherical coordinates. So in spherical coordinates, I'm going to have 3. My function is going to have to be switched to the correct coordinates, but I'm also going to have to include rho squared times the sine of phi. So whatever the function brings to be integrated, I have to multiply it by rho squared times the sine of phi and integrate all that stuff along with it. Otherwise, our d theta and our d phi are not going to be lengths. So this factor is there to turn, let's see, d phi, d theta, d rho into lengths. So the way I set it up here, man, I hope there's not a more convenient way to do this. I need to integrate rho between 2 values. I need to integrate theta between 2 values. And I need to integrate phi between 2 values. I want to capture the whole sphere. So what values of rho are going to describe all the points in this solid? What's the smallest value of rho? Rho has to be positive. Them's the rules. Rho has to be between 0 and infinity. So remember, we want this whole thing. So the surface of the sphere is where rho is equal to 3. So that's where the sphere ends. And I want everything up to 3. So I want to start here I want everything, say, starting at the origin up to the z-axis, because I want rho to always be positive. So we're going to describe rho as going from 0 to 3. That goes in all directions from the origin to 3 units away from the origin. Rho has to be positive. What values of theta will we need to describe this sphere? We look at this from the top down. I want theta is measured from the positive x-axis. So I want theta equals, and theta has to start at 0. That's the lowest value we're allowed for theta. And I want theta to go all the way around. So I'm going to integrate theta from 0 to 2 pi. Because I want to get every slice going around the xy plane. And for phi, I want to go from the positive z-axis all the way down to the negative z-axis. But that's where we run out of phi. So phi just goes from 0 to pi. So in spherical coordinates, a sphere is a rectangle, has the same integral setup as a rectangle in rectangular coordinates. So that's cool. If I only wanted an orange slice that encompassed the first quadrant in the xy plane, I would just integrate theta from 0 to pi over 2. If I wanted the left half of the sphere, I would integrate theta from 0 to pi instead of from 0 to 2 pi. If I wanted the top half of the sphere, I would just integrate, phi goes from 0 to pi to get the top half. The bottom half would be from from 0 to pi over 2. If I want the bottom half, I would just go from pi over 2 to 0. If I wanted to hollow out the sphere, I don't know if you've ever heard of the hollow earth theory. People used to think that I don't know if they really thought this or just some science fiction writer wrote it, and people said, oh, that must be the case. And so there was the idea was the earth is hollow. There's just like this shell, and then there's like this whole world underneath. Yeah, Jules Verne said it, so it must be true. He's a smart guy, so it must be true. Incidentally, that's like a super damaging thing that we always do. Some smart guy says something dumb, and we just run with it. Anyway, so Jules Verne is like, well, yeah, the Earth is actually just a shell on the outside, and then there's like this whole hollow space in the middle. So if we wanted to hollow out the center of this sphere, it's also not a sphere, but let's round out the Earth. If we want to hollow out the center of the sphere, instead integrating from rho to 3, all the way, make it solid from all the way from 0 out to the edge 3, I could just integrate from 1 to 3. Then I'd hollow out a sphere of radius 1 inside the center. So if let's say I just wanted the orange peel, then I could integrate from, say, 2.5 to 3. So that would just be this shell, spherical shell, half a unit thick. So a good exercise here would be to imagine, how would we integrate hollow earth style? Top of the sphere. Let's say the left side of the sphere. I knew I'd remember the word eventually. The left hemisphere. What if we had the left hemisphere only on the top? Hemisphere? Half a hemisphere? Let's say, yikes. I'm putting words all in the wrong order. It'd be cool if I was actually turning into Yoda, but it's only my language that's turning into Yoda. So let's suppose we want the top half of the left hemisphere. So what you can do is take this triple integral that describes the entire sphere, and just start breaking it up into pieces. What if we wanted to integrate hollow earth style? That's an adjustment to rho. If we wanted the top of the sphere, the top hemisphere, that's going to be an adjustment on phi. The left hemisphere will be an adjustment on theta, because I got the left and the right. What if I want just the top half of the left hemisphere? That's an adjustment to the top half adjustment of phi, the left side, and adjustment in theta. What if I wanted the top half of the left hemisphere of a hollow Earth where the outer shell is 1 unit thick? Top half, left hemisphere, 1 unit thick, outer shell, hollow Earth. How can we adjust all these values? Any questions? So imagine what the triple integrals would be to describe those different solids. And remember, when we actually get down to integrating the function, we have to include this extra rho squared sine phi. We need the rho to turn phi into a length, and rho sine phi turns d theta into a length. I could have shortened that whole talk yesterday just by saying, put this in there. And then people would have been, why? And then I would have been, because I said so. That would have been a very 80s style explanation, where it's like, oh no, I've got to get you to just do these things. And then students will be like, oh, but I want to understand what's going on. And then the professor would be like, oh, that's a lie. You just want me to credential you. And the students will be like, oh, yeah, that's true. So memorize these things, because this is the 80s and we've got to beat the Soviet Union. What I'm saying is that there was a lot of propaganda in the 80s and people my age were subjected to it. But it's okay. We were just young and impressionable, and oh, damn it. That's probably going to cause some problems in the future that we're living in right now. Oh well. Any questions? Comments? All right, now is the tricky one. Now we need to start describing what's going on in cylindrical coordinates. I saved the most fun one for last. Mostly because we can't be using x, y, and z to describe things in cylindrical coordinates because there is no x and y in cylindrical coordinates. In cylindrical coordinates, this is going to have to get adjusted to use r, theta, and z. So here's how to do that. Ah, dang, look at the time. I guess we're going to have to leave that as an exercise to the reader. There is no x and y, only r and theta. So the polar coordinates r and theta are Joule now. All right, let's pause the video here and talk about next steps.